Welcome, everyone. In this video, we will create a machine learning model using the VGG16 transfer learning architecture. We will see how to load the dataset, pre-process the data, create models, and evaluate their performance. We will also see how to persist the models to disk. So without further ado, let's begin. To start, let's talk about the dataset. We will be using a household waste classification dataset that has 30 classes ranging from cola bottles and styrofoam cups to newspaper, magazines, and pieces of clothing. Each class has 500 images, 250 regular images, and 250 images in real-world setting. Since this is a pretty large dataset, and we will also be performing data augmentation so that you know how to do it when the dataset isn't this big, for this project we will use just 5 classes. These classes are plastic soda bottles, disposable cutlery, styrofoam food containers, eggshells, and aluminum soda cans. Depending upon your application, feel free to choose different classes and/or add more classes to the dataset. We have added the link to the dataset and the 5-class machine learning model file in the Resources section. The Resources section also contains the Kaggle notebook for this project. Kaggle provides 30 hours of free GPU per week that is reset every Saturday. So if you start on a Thursday, you should be able to run the complete notebook for yourself by the end of the weekend. With that out of the way, let's start with the actual code. This first line of code is added by Kaggle when you create a new notebook. It imports a few libraries and then prints all the files available in the dataset. As can be seen, our files are located in the location Kaggle/input/images/images. We will use this location later when we want to transfer files to the working directory. With that done, let's import some libraries that we will need to build code. We will use OS, sys, and shutil for checking a directory's content, creating new directories, and moving and copying files during data preprocessing. Shutil will also be used during the persistent stage to generate zip files from folders. PIL library will be used to create an image object and to apply data augmentation techniques like brightness and contrast modification. TensorFlow will be used to build models, and finally, scikit-learn and matplotlib to evaluate and visualize model performance. With that done, next we configure some variables and paths for our project. For now, we will set epochs to 200 and batch size to 128. These are pretty standard values. And from our experience, most people start with these values and then make modifications based on their model's performance. We will also set the train test split to 0.9, since our dataset is pretty big, and with this split, we should get more than enough images to test the model. Some other popular options are 0.8 and 0.7, and the choice will depend upon the size of your dataset. Next, for data augmentation using brightness and contrast modification, we use just one value, which is 2, as it usually works well. But feel free to use any number of values for your use case. Most people choose values between 2 and 5. Value of 1 means no modification, and values greater than 5 usually distort the images too much, making them unusable. Next, we set 0.85 as the value for the learning rate scheduler, and 0.625 for early stopping. We have been making models for a long time, and these values usually work well for us, and we would suggest that you keep them as is for now and make modifications later on as per your needs. And finally, we set paths for the input dataset and the outputs, like the train, test, and the saved model folder. With that taken care of, let's start with the first data preprocessing step, which is copying the files from our dataset into the working directory. This is done because the Kaggle input directory is read-only, and we want to do data augmentation later on, which will require creating new files. To copy the files, we first create new folders inside the working directory for each of our 5 classes using the OS library's make_dirs method. The exist OK parameter is set to true so that the code just moves on if a directory of the same name is already present. We then create a list of all classes from the input directory and modify these names by replacing the underscore with the hash. This will help us later on when we are doing data augmentation and also when we want to move the files to the train and test folders. Next, we check if these modified class names match the names in the selected classes list, which contains our 5 selected classes. And if true, two lists, one for each subfolder, are created, containing the names of all the image files of that class using list comprehension. We chose list comprehension as it is super fast as compared to loops, and would suggest you do the same. Finally, we read each file in the two file lists, change their names so that they include the class that they belong to, and then transfer them from the input directory to the new folder. Here, src, or source, represents the old path, and dst, or destination, the new path where the file needs to be copied. This one specific folder for each class is a TensorFlow requirement for image classification, and it uses it to distinguish between the different classes. Let's run this now. This can take a couple of minutes, so we will come back when it's ready. Okay, the code run is now complete, and as you can see, the size of the working directory has increased to 150 plus megabytes. And so the files have been copied, but let's do a sanity check by counting the number of files in each folder. This code in the next cell does this. We also create a final file list and a class list that we will use in the next step when we are doing data augmentation. The final file list contains paths to all the image files, and we create it by first creating a list of directories inside the base working directory, and then running the list_dir function on each of these directory paths and collating the results. And so if we run this cell now, we will see that there are 500 images in each of the 5 class folders for a total of 2,500 files. Nice. Let's now augment this data so that our models can generate some decent performance. Let's first perform contrast and sharpness modification using the PIL library. For this, we read each image file, perform the contrast and sharpness enhancement using the Image Enhance module's contrast and sharpness classes, create a new name, and finally save the files in their respective class folders. Do note that there are 2 more classes available in this Image Enhance module, the Color and the Brightness class, and I would encourage you to try these out as an exercise and assess their impact on model performance. Running this cell also takes a little time, as we are effectively doubling our dataset size, but once it's done, you will see that the working directory size is just over 300 megabytes. Okay, now that we have our augmented dataset, let's split it into train and test folders. For this, we will do 3 things. First, we will create a new final file list, which lists all the image paths post-data augmentation. Second, we will create new train and test folders. And finally, we will move these image files from the raw folder into these train and test folders. This next cell does these 3 things. For moving the files, we first create a counter and a list of files belonging to a specific class. Then, if the counter value is below the test train split value, we move the file to the train folder using Shutil library's move command, else we move it to the test folder. Note that both the train and the test folders need to have 5 folders each, 1 for each class, like before. Once we run this, we will see that we now have 1,000 images for each class, for a total of 5,000 images, and that we have successfully split them into train and test sets. With the data split and ready, we next perform the last step in the data pre-processing pipeline, which is the creation of a data generator that will feed our data to the model. For this, we use TensorFlow's Image Data Generator class. This class, in fact, does 3 things. It performs data augmentation using techniques like rotation, shear, flip, zoom, etc. It also has support to perform last-minute data pre-processing, like changing the image type to float and normalizing the images. And finally, once all this is done, it pushes the data to the model. Coming to the code, you will see that we created 2 data generator objects here, one for the train dataset and other for the test dataset that we are calling validation here. During data generator object creation, we pass values for different data augmentation techniques. Feel free to play around with these values to see what generates best performance for your case. The values that we have here generally work well for most cases. We also pass this object a function to perform some last-minute data pre-processing. This is a highly recommended step by TensorFlow when performing transfer learning. As you can see, we use the ResNet preprocessor function here, but feel free to choose a preprocessor function from any one of the architectures, as they all do almost the same thing. Coming back, Once we have created the DataGen object, we pass to it four things: the path containing the images, the size of the images, the batch size, and whether we are performing binary or multi-class classification. The transfer learning architectures that we have chosen accepts 224 by 224 images, so we add that here as well. For the validation or the test DataGen object, we need to set an additional parameter, the shuffle, to false. If not done, the order of the images and the labels that are fed will be shuffled, resulting in incorrect model performance evaluation. And that is all. Once we run this cell, you will see that both the DataGen objects have been created and are ready to push the data to our models. Now let's talk about model building and evaluation. As we have seen before, there are a few things to do when building models. We design the model architecture, we tell the model the optimizer and the loss function it should use, and the evaluation metrics on which it should evaluate model performance. Apart from these, the TensorFlow library also gives us the option to refine and track our training process using something called callbacks. Some of the more popular ones are changing the learning rate using a scheduler, stopping the training process early when we detect overfitting, and periodically saving the model weights so that if the training was to stop abruptly for some reason, we don't have to start from scratch. In this project, we will be using all three. But as always, feel free to explore and use the ones you feel are more relevant for your use case. In this next cell, we create a learning rate scheduler and an early stopping callback. We also create a few variables like class list and unique images per class, which we will use when naming our model. The learning rate scheduler is pretty straightforward. We create a function which checks if the number of epochs is greater than a threshold and, if true, reduces the learning rate by the value e to the power minus 0.1. You can use a calculator and see that this roughly translates to 0.9, or in other words, at each epoch after the threshold, the value of the learning rate would be reduced by roughly 10%. For the early stopping callback, we have defined a class called myCallback. You can create any logic you like, but we have kept it simple. In our function, we check for two things: if the number of epochs is greater than a threshold, and if the difference between the training and validation loss is greater than 5%. If it is, and if it has been for the last 10 epochs, we stop the training. The threshold makes sure that a certain level of training has happened before we check for overfitting. We also want to make sure that this large difference in training and validation losses isn't a one-off thing, but a recurring phenomenon, which is why we added the check for 10 continuous epochs. On running this cell now, we see that there are 900 images per class in the training set and 100 images in the test set, which is correct. We also confirm that there are 500 unique images per class. Next, we create a plotting function using matplotlib that will display the losses and accuracy of our model over the training process. The function uses the training history for this. Also, we have coded the function in such a way that if you wanted to visualize any other metric apart from accuracy, you could do that too using the key parameter. Let's run this cell now. Okay, done. Now, in this next cell, we have two functions. One to evaluate the model performance, and another to store the performance data in a separate text file so that you have one place where you can go and look at all the model performance data in one shot. The display performance metrics function makes prediction on the test or the validation data and then evaluates and displays the performance using scikit-learn's class report and confusion matrix functionalities. The save performance to file function is the one that saves the performance data to a text file. Okay, let's run this cell. Next is the fun part, the designing of the model architecture, and we will use VGG16 as our first transfer learning architecture. As you can see, the base model requires three pieces of information: the input image size, whether to include the top layer or the final dense layer with softmax activation, and the type of weights to use. For the image size, we use the standard 224 by 224 size, and this should match the size that you mentioned in your data generator. Since we want to do training on our custom dataset, we set the include top parameter to false. This way we can add our own layers at the end of the model with number of neurons equal to the number of classes. Also, since we want to do transfer learning and not learning from scratch, we set the weights parameter to image-net. With this, we get all the learnings from the ImageNet dataset, and we just need to tweak the weights of the final layers a little bit to make the model fit nicely on our data. Next, we add 2 layers on top of the base model: a global average pooling, or GAP layer, and a dense layer. The GAP layer kind of collates the learnings from the base ImageNet VGG16 model, which are then used by the dense layer to make prediction. As we discussed previously in the machine learning section, since this is a multi-class classification problem, we use the softmax activation function and the number of neurons equal to the number of classes, which is 5 in our case for this last layer. Next, we set the input and outputs of the model and freeze all the layers except the last 4. This is done so that only the weights of the last 4 layers are tweaked during training. Or in other words, skipping this step would tweak all the weights in all the layers, resulting in a massive loss of learning that happened when the model was trained for a long time over millions of ImageNet images. With this done, we finally compile the model by adding the optimizer, the loss function, and the evaluation metrics, which we have chosen as accuracy, precision, and recall. We end the function by adding a line to display the model summary for those of you who would like to explore the different VGG16 layers and the number of parameters in each one of them. For this first run, we will choose the SGD optimizer and add a model checkpoint callback, which saves the model with the best validation loss, and then start the training. With our setting of freezing all but the last 4 layers, out of roughly 14.7 million parameters in the VGG16 architecture, only 7 will be trained, while the rest will be frozen. Also, as you can see, the model training has started, and it should roughly take 3 to 3.5 hours on a Tesla P100 GPU to train. So we will cut the video here and come back when it's done. Okay, the training is now finished, and our model is ready. As you can see, we got an accuracy of around 96% on both the training and the test data, which is good, but I believe we should be able to do better. Let's explore the training graph now. It shows that the training went well, with both the validation and the training loss reducing gradually and finally plateauing around the 0.2 mark roughly. Similarly, the accuracy graph shows that the value increased rapidly until 0.8, at which point it slowed and then gradually plateaued. Okay, let's now load the best model and see how it performs on the test data. As we can see, the model did fairly well, getting an overall F1 score of 0.96 with slight dip in performance for Class 3. The confusion matrix below provides more detail on the performance across different classes. Looks like for both Class 1 and 2, the model got a few of the images confused with Classes 3 and 4. And this is fine. Let's now run this VGG16 architecture with 2 other optimizers that we discussed in the deep learning section, the RMSprop and Atom. This should take roughly 7 hours. We will come back when these are done. Okay, both the models are now done. For the RMSprop model, we got an accuracy of greater than 99% and an F1 score value of 0.99. The training went pretty smoothly, mostly. We got a rapidly decreasing loss and a rapidly increasing accuracy in the beginning, which then slowed down and plateaued till it hit epoch 182. At this point, our early stopping callback kicked in and stopped the training as the model was starting to overfit. Coming to the evaluation metric part, we see that the model got perfect precision and recall scores for classes 0 and 2, with classes 1 and 3 not far behind. The score was slightly low for class 4, as it got a couple of predictions mixed with class 1 and 3, as can be seen from the confusion matrix, but overall, very decent performance. Moving on to the model with the Atom optimizer, this one too got an accuracy of 99% and an F1 score of 0.99, but the training was slightly more jerky. Also, the early stopping callback kicked in at epoch 154 to stop overfitting. The model got perfect precision and recall scores for classes 1 and 4, with slight below-par performance for class 0, which it got mixed up with class 3, as we can see from the confusion matrix. But again, pretty nice performance. If you are satisfied with the performance and want to save the model to disk, it is pretty straightforward as well. Click on Table of Content in this bar on the right-hand side, and then click Model Persistence to go to the Model Persistence section. Here, add the name of the model you want to save to the model path, and the name of the saved file to the save file path, and run the cell. Shutil's Make Archive method will create a zip file for you in the output directory, and you can go there and click on the 3 vertical dot button to download the file. And that is all for this video. In the next video, we will look at another transfer learning architecture called the Inception. See you there.